Consider a hot surface losing heat to a surrounding fluid. Newton's law of cooling says the heat rate equals H times surface area times temperature difference. The convection coefficient H is fixed by the fluid. Temperature difference is set by the application. Surface area is what we can engineer, so we attach fins. Fins. Thin extensions attached to the surface. Multiply the area without changing the footprint. More area means more heat rejected. Here are the four main fin geometries, shown side by side. Rectangular fins have uniform cross-section, simple and common. Triangular fins taper to save material while keeping good performance. Annular fins radiate outward from a cylinder, used on engine cylinders and pipes. Pin fins are small cylindrical protrusions, ideal when flow comes from multiple directions. Take a thin element of thickness dx along the fin. Heat enters by conduction on the left, and exits two ways. Conduction continuing right, and convection off the surface. Setting inflow equal to outflow gives the energy balance. Applying Fourier's law. Heat flux equals negative K times area times temperature gradient. Convection from the lateral surface equals H times perimeter times dx times excess temperature. Substituting and simplifying gives a second order ode. Define theta as excess temperature above the fluid, and m squared as H times perimeter over K times area. The result is the fin equation. Second derivative of theta minus m squared theta equals 0. Where m equals the square root of hp over kac. P is perimeter, k is conductivity, and ac is cross-sectional area. With an insulated tip, the temperature profile is a ratio of Koch functions. Watch the split screen. On the left, the fin color updates live as we change ml. On the right, the temperature curve updates simultaneously. At low ml, the fin is nearly isothermal. Temperature barely drops. As ml increases to 2 and then 4, the drop becomes steep. The tip approaches the fluid temperature. The fin is doing maximum useful work. Fin efficiency compares the actual fin to a perfect fin held entirely at the base temperature. For an insulated tip fin, efficiency equals tan H of ml divided by ml. Let's watch a dot trace the curve from ml equals 0 to 5. At small ml the fin is nearly isothermal, efficiency close to 1. As ml grows the tip cools and efficiency drops. The practical design target is ml below 1, giving efficiency above 76%. Effectiveness compares the fin to having no fin at all. It's the fin heat transfer divided by what the bare base area would have transferred. For a straight fin with insulated tip, effectiveness equals the square root of K times perimeter over H times area, times tan H of ml. The rule of thumb, only add fins if effectiveness exceeds 2. The Biot number being much less than 1 confirms fins will work well. Fins work best with high thermal conductivity like copper or aluminum, low convection coefficient like natural air, and a large perimeter to area ratio. In practice we use arrays of fins, not just one. The total area includes n fin surfaces plus the bare base area between them. The overall surface efficiency accounts for both contributions. Total heat transfer from the array equals E to O times H times total area times base excess temperature. When fin efficiency is 1, overall efficiency is also 1. We recover the simple limit. Fins are everywhere once you know what to look for. Uses aluminum fins with forced air convection to keep processors cool. Motorcycle engine cylinders use cast fins in natural convection. Large area compensates for low H. Car radiators use corrugated fins between flat tubes, handling large heat loads compactly. These 5 equations form the complete toolkit for designing extended surfaces. Here is a challenge problem. Given these parameters, calculate ml, efficiency, and effectiveness. Try it.